Okay, so here I have a bunch of equations when it comes to electrochemistry. First we have delta G equals negative RT ln KQ. Delta G equals delta G naught plus RT ln KQ. Delta G naught equals negative NFE. F is Faraday's constant, and E is the the E of the cell. Delta E equals delta E naught minus RT NF. Again, this is Faraday's constant. I usually approximate it as 10 to the 5th, although that's not exactly the number, but it's easy for me to approximate things. So I approximate it as 10 to the 5th. And then we have ln Q. Another way you can write this is as delta E minus 0.06 over N. I rounded this, it's usually 0.059 around there, but at standard conditions, you can just assume that this whole thing turns out to be this value. And of course, it's easier because now you have log Q instead of ln. Okay, if you want to figure out the amount of something that is plated, the number of moles of, for example, of sodium that is plated onto the anode, then you would do this equation. I usually remember it as it is not fun. I is current, T is time, N is the number of moles of electrons. Like for example, in this equation, it would be 2 because we have 2 moles of electron, and F would be Faraday's constant, which is 10 to the 5th. Here is the cell potential, the membrane potential actually, the membrane potential, which is around 60 millivolts over N log Q. Again, I use this version because this is assuming it's at standard conditions, which means it's at 25 degrees Celsius, 1 mole and 1 atmosphere. So the E cell equals E of the reduction minus E of the oxidation. You use this equation if all of the E givens are the reduction potentials, okay? If you're given an oxidation potential and you want a reduction potential, you just reverse the sign. You just do the negative of that. Also, taking into consideration that potentials, you never multiply by the number of moles. This is something that you do with enthalpy and others, but do not ever do this with the with the potential. Okay. Also, we know here Ohm's law, V equals IR. This is resistance, rho over LA. Higher resistance with higher temperature. This is power, I times V, voltage. I is current. This is voltage equals the electric field times the change in distance. Also, take into consideration R, I usually round it as 8. Okay, so the voltaic cells are usually very spontaneous. That means delta G is negative, and E is always the opposite of delta G, so E is positive. For a concentration cell, it's spontaneous, and then E naught is always equal to 0. Okay, because usually this happens under standard conditions, and when you have the same number of moles of the same reactant, like sodium and sodium, same number of moles, they're going to cancel out to 0 when you're doing the calculation. And for electrolytic cells, the exact opposite of voltaic cells, non-spontaneous, so that means delta G is positive, and the potential of the cell is smaller than 0, so it's negative. Also notice that for a voltaic cell, you use a salt bridge. And for an electrolytic cell, you're trying to do a non-spontaneous reaction, you need to have some kind of input, so that we use a voltage source to supply that energy, that voltage, to make the reaction go to where you want it to go.